Aloha, Richard Halverson here. This is ITS148, and today is February 16th, it looks like. And let me share my screen. And so here we are. Let's see the syllabus. Let's look at the syllabus. We are in chapter 14, recursion. We're in week 6. And so we're going to go through chapters, or we're going to try to get through the whole chapter today. We might not, just because it's kind of difficult to explain recursion. So it may be better if I took two class periods to explain this, but we'll see how it goes. Okay. So chapter 14. All right, recursive functions. Okay. A function, as you know, can call other functions. That's what a function is. And a function can also call itself. And when a function calls itself, or if a function can call itself, it's called a recursive function. Okay, so usually a recursive function ends up calling itself, several times, because it calls itself, and then inside, it calls itself again, and it keeps on calling it. So there has to be some condition. Each time it calls itself, there's got to be something different, and there also has to be a condition where eventually the condition will be met where it won't call itself. And once it doesn't call itself, then it starts to return and sort of pops back out again, and then it ends up finishing. So here's a real simple dumb example just to explain kind of what recursion is. Okay, so let's say you have a function here. It's called countdown. Let me make it a little bigger. Oh, it's pretty big. Okay, so it's called countdown. And let's see, can I close this? And the parameter that it's called with is 2. Okay, and so here's the definition of countdown. Okay, it comes in. Let's see, it's an argument here. It's a parameter here, and so the parameter is count. And if the count is 0, it does one thing. If the count is not 0, it does something else, which includes calling itself. Okay, so but notice when it calls itself, it changes something. It takes what came in as count and subtracts 1 from it, and then it calls it again. So the next time it comes around, it's not going to be 2, it's going to be 2 minus 1, so it's going to be 1. Okay, it comes in as 1, it's either going to do this or it's going to do this. In the case of 1, it's going to do this again, but then it's going to call, and it'll call itself again. But this last time it'll subtract 1 from 1, and this argument will be 0. So it calls itself with a 0, with an argument of 0. Well, when that thing comes in, it's going to come in. Now, since count is equal to 0, it just prints out the word go, and then it quits. So you have to recognize here that if it's okay, so it's going to execute either this if part of the block, or the else part of the block. And when it's done with the if part of the block, or it's done with the else part of the block, it's going to go down to here, which is the end of the function. So then it returns. So the two things that you have to notice about this is when it returns, it's done. It returns back to the caller, and each time it's called, and if it calls itself again, it calls it with a parameter that's different. That's going to eventually lead to the parameter that will terminate the recursion and start this return process. So when this is done, then it jumps down to here and it returns, and it's going to return to right after this because this is what called it. Okay, and so when it's done calling it, it drops down to here, which means it returns, and it returns back to the caller. And in the second case, this is also the caller, and it's done calling it, so it drops back down to here. And then when this is done, the third time it returns, and it's not going to return back to this one. The last one is it's going to return back to this one. So then it proceeds down. And so what we see happening here is each time it's called and it's not, and the argument is not 0 each time, it just prints it out, and then it calls it again. So that's why we see this here, where the first time it's called, count is equal to 2, and then the second time it's called, count is equal to 1. The third time it's called, count is equal to 0, and each time it's called, it prints the 2, it prints the 1, and then it comes back around, and it's this case, so it prints go. It doesn't print 0, it prints go. So it prints go, and then it returns to here, and then it returns to here, and returns to here, returns to here, and it returns to here, and finally it returns to down here. So when it reaches this point, then it's going to have to, when it reaches this point, then this thing executes and go is printed, and then it pops back up to it pops back up to this one, and then that function that method just quits. Then it pops back up to this one and to this call, and that's this one, and then it quits. So anyway, that was kind of a long explanation of recursion, but I hope you get the idea with this very super simple program. Now you can do the same thing with a loop. You know, you can oftentimes take a program that's really a loop, that's got a loop in it, and you sometimes can write a recursive program to do the same thing. Also, if you have a recursive program, then you can almost always write a non-recursive program that's just a loop. Okay, that's got an iteration. And in this case, for example, the loop would be, first, start out at 2, print that, subtract 1 from it. Is it 0? No, print that, subtract 1 from it. Is it 0? Yeah, okay, print go, and then you're done. See, so anyway, so this here tests your understanding of the algorithm, and you'll notice when you load a 2, or when the first argument is 2, then countdown executes 3 times, twice printing the number, and then the last time it hitting 0 and it printing go. So when this is 2, it executes 3 times. If this is 5, I bet it executes 6 times. Okay. Yes. All right. How many times is countdown called if the script calls countdown equals 0? Well, it says 0 plus 1 is 1. It's always 1 more, right? And then is there a difference in how we define parameters of a recursive versus a non-recursive function? No, there's not really a difference in how we, there's not really, okay, there's a, okay, so Aaron just asked, what is better, a loop or a recursive for ease of use? Well, I'll just tell you, a loop is probably always better. It's probably always better to do a loop. There are a few times when, well, a recursive solution is usually more elegant. It's usually more, clever and, intellectually interesting. But rarely do we actually write recursive programs or a recursive method in a production program, unless it's a application that really truly does adapt itself to a recursive solution. One is the evaluation of an expression. Okay, so in an expression, you have, you know, parentheses, and you can have an expression inside parentheses, inside more parentheses. You can have this nesting of parentheses. You can have an expression that's got, like, you know, five nests deep of parentheses. You know, you could, and it turns out that a recursive algorithm, it's called a recursive descent algorithm for recursively evaluating expressions, that works out real well. And I'm you know, many compilers, I mean, the Python interpreter probably has a recursive descent method in there to evaluate, you know, the right side of an assignment statement to evaluate an expression. But anyway, unless it's clearly obvious. Oh, also, if it's obvious, it's probably going to be something that you find on the internet, and you start with that. You know, you like, let's say you have to write a parser to evaluate an expression. You'll look on the internet, you know, parser to evaluate expression, and you'll find it, and there'll be variations, and it'll be written in some language, and you'll translate it into the language that you're, you know, writing your application in. And so there, it's so a lot of times it's just a matter of understanding it first. But there are some interesting algorithms, like finding the greatest common divisor of, you know, between two numbers. That's nicely handled as a recursive algorithm. Sometimes it's a good exercise to write, you know, to start out by writing the non-recursive version, and then you write the recursive version to see the similarities and so on. But anyway, so we're gonna study recursion in this chapter, and we're probably not gonna, you know, see too much of it again. You know, actually, traversing trees is another time when a recursive function can be handy, because you know, a tree is defined. You know, a tree the tree data structure is defined as a node with a left tree and a right tree. So a tree is defined as a, you know, it is defined in terms of a tree. So when you're traversing a tree, you know, it's convenient to express it as a recursive function. So
I had a question again, sorry.
Yes.
So is a recursive algorithm shorter code than a loop?
Yes, it generally is,
Because it looks like it's just, you know, a lot shorter than looping.
Yes, yeah, it's nice and compact. Yep. Yeah, it's sort of, you know, you kind of have to wrap your mind around it. And the reason we can have recursive algorithms or recursive methods is because of the way programming languages are implemented now. When a method starts running, when a method starts being executed, the variables inside the method are the space for those variables are sort of created or allocated at the time that the method is called, and then when the method is done, they are released again. Okay, so they're not used anymore. And so when a method calls a method, which calls a method, there's this thing in there called a stack. And I think, have we studied stacks? Anyway, a stack is like a, you know, last in first out thing, and so these blocks of memory that contain the variables inside of a method, is that block of memory is allocated on the stack. And then so this method, a method calls another method, and that block is allocated on the stack, and then that method calls another method, and that block is allocated on the stack. And then when it returns, this block can go away, it's not needed anymore. And then when there's another return, this block goes away, and the memory shrinks back down to, small again. And so because that's sort of a natural, a good way to allocate memory when executing a program, it's sort of naturally, it lends itself nicely to recursion, because each time there's a call, there's a new block of memory that's allocated for those variables, and that block is different than the previous one. So even though like the name of the method is the same, it's a different block, and the variable names and everything are the same. It's a different space because it's a different block allocation. And in the old days, before they got smart and started implementing sub-programs or subroutines or methods or procedures or whatever you want to call them, before they got smart and started allocating that memory from a stack, before they weren't smart enough to think about a stack. They just allocated it in plain memory. So you have a method there, and it uses these 5 variables. Well, these 5 variables are going to be location 100, 200, and 300, and that's it. So then a recursive program is hard. You can't, because when it calls itself, it's got the set of variables. It's got to be a different set of variables. It's got to be a new set of variables. And the old way of allocating memory for a program, just allocated it once, statically. Once it reads the program, it's there's 10 variables in this whole program. Doesn't matter if there's some of them are methods or not. We allocate that. And so back in the old days, before they even thought about recursion, back in the 50s, everything was iteration. And they figured out very early in the 40s, they figured out what a minimal kind of computer would have to be for it to be able to compute anything that could be computed. Okay, and recursion is not in there. It's like you have to have a subtraction function. You have to have a jump if the evaluation of the expression is negative, and you have to be able to jump to a particular spot in the program, and that's about it. Okay, it's kind of a long answer to your question, but recursion is a good thing to learn how to do and understand. So when those few times, those few chances you have to use it, you'll know it, and it'll be kind of cool. Oh, I can use recursion here. Okay, so how'd that work again? You go on the internet. In the old days, you pull out a book that you had back in college, but now you just go on the internet. Okay, and then you get it to work, and it's usually small bit of code, and so, but I think we're going to end up writing and seeing some algorithms that are written both ways, and you'll see some, you may find that recursion, a recursive method, is really easy for you to visualize. And if it is, yeah, go ahead. There is a little bit of a performance penalty that you pay for recursion, having to do with the step of allocating the memory location, allocating the memory variable space on the stack. Each time you do a call, for a recursive program, instead of looping, you call a function 5 times instead of looping 5 times. Well, calling a function is a little bit more expensive than just jumping, because you're skipping the if part. You jump over the if part to execute the then part or the else part. That's really fast. But jumping, to call a method, that's expensive, because that call involves that stack thing that I told you about, allocating the memory locations and so on. So anyway, let's see, it's 3:51. All right, let's see if I can get through some sections. All right, does that kind of answer? Did that kind of answer your question?
Yes, thank you. It looks like it might, I see what you're saying about the memory allocation.
Mhm. Right. Okay, so so we just got done stepping through the, okay, so this is a calling a recursive function. Write a statement that calls the recursive function back. We have this function called backwards alphabet. So it starts where it takes an argument as f, and then it's going to just print out f, e, d, c, b, a. Okay, so, and we're supposed to finish this program, I guess, here. Okay, so we have this function, and well, do we just need to write the statement that calls it? Okay, this is kind of dumb. Well, I think the statement that calls it is backwards. F, right? Because we're starting out with F. We start out with F, comes in here, is the current, and that would be F. This is F. When the first time it comes in, is the current letter A? No, it's not. So come down here. Okay, first thing you do is print it. Okay, so we're going to print the F. I'll print the F. And then we're going to go down here and we're going to calculate this previous letter. So you know, we want E. Okay, so what do? We take F, we take the ordinal value of F, and what the ordinal value is you know, you have ASCII table, lowercase f is character f. F is here's F right over here, and it's so 102. Is that the decimal value of a decimal value of F is 102 F, and so that's what this is. This is going to be 102. Subtract 1 from 102 and we get 101. So this is 101. What's 101 is the E. 101 is E. So that's going to be, so the character of ordinal value 101 is E. So this thing is going to be E. So this is E. So now we're going to call the function with E. Okay, comes back around. First thing it does is it A, no, prints it. So prints the E. And then it keeps on doing this until finally it's B, and B minus 1 is A, and this prints, it comes in and it says, is the current letter A? Yes, it prints the current letter, but then it doesn't do any of this stuff down here. It's done. Jumps down to here. It goes from here, and after it's done printing the A, it comes down to here, and this is the end of the program, so it returns. And where does it return? It returns right here just after it called it with A. Okay, so it's done doing what it does with A, and then this returns down here, and then so this causes a return, which is going to cause, you know, the return here from when it called from B. You know, it was in B, which made this A. Anyway, it keeps on returning until it's done. So by the time it prints the A, it's done printing, but it's 6 deep. It's 6 deep down in calls. But all it does is return. See, so that calling is, I mean, this is nice and elegant, but that calling is what can be expensive. Calling, then you return, you reallocate, and by reallocating, it doesn't look like we're reallocating much. There's some housekeeping stuff that takes place here, but really the only variable is like this variable. It's got to go. This variable. This is a new variable. So each time this is called, it's got to create a new one of these. Okay, so by the time this thing is printed, there's going to be 6 versions of prev letter sitting around. The A is gone, but the B is still going to be in there, and the C is going to be in there. And as the thing returns, then they get returned back to the free memory list. All right, so, but this isn't quite right, because this should be, it looks like it reads in starting letter, so this should be copy. This, I guess it should go right here. Because you read in starting letter and then it's gonna. Okay. All right, so so that's that. What's next? That's section 2. Okay, recursive search. Okay, so here we're talking about this is actually a pretty good an algorithm that's pretty good. Which you could write either way. It's still probably better to write it as an iterative algorithm, but when you're doing a binary search, you've heard of binary search, and here we're gonna, next 2 sections are gonna be talking about binary search. You can see how it's nice. It's easy to explain it. It's kind of easy to explain a binary search use recursively, but again, if you're actually implementing it, you're going to have this this nesting of calls going on. And although it's not going to get very deep, if you're doing a binary search on a million records, that's you know, a million is like 2 to the 20th power, right? It's about 2 to the 20th. Yes, 2 to the 20th is about a million. 2 to the 30th is about a billion. So a binary search to find something in a million records would take at most 20 tries, okay? Because it's the log to the base 2 of a million. It's the reason I say 2 to the 20th equals a million is because 20 is about log to the base 2 of a million. So anyway, I think I'm getting into too much detail here, but you'll see what I'm getting at after we finish these next 2 sections. Okay, so here we're trying to again trying to understand the concept of recursion, and so here we got 2 algorithms, and I've always thought this is a good way to teach algorithms, where you know, it's instructions on how to do something in everyday life. Making lemonade, it looks like this, but each step is distinct. But an algorithm for mowing the lawn might not be. Okay, so you mow the lawn, and mowing the lawn means mowing the front and then mowing the back, and then mowing the front means mowing the left and mowing the right, and mowing the backyard, it's the same, mow the left and mow the right. So we see there's this kind of recursion thing going on, and with each call, you know, this mow consists of 2 mows, and each mow is half the size. Okay, and then this mow here also consists of 2 mows, and each mow is half the size of this. So this is kind of, you know, this way of breaking it down, and then you're breaking it down into smaller and smaller, you know, tasks, and then once all the little small easy tasks are done, then we see that the whole thing ends up being done. Okay, so here's another example of how they're trying to explain it. Let's say, you know, we play a guessing game, and I'm thinking of a number between 1 and 100, and you're going to guess, and you're going to start guessing numbers, and I'm either going to say it's higher than that, or I'm going to say that's the number, or I'm going to say it's lower than that. Okay, so basically, let's say we start with let's say it's 100. Let's say it's 100. Numbers, and you're going to tell me a number, okay, and then I'm going to either say, yeah, yes, that's a number, or I'm going to say it's in the bottom half, or it's, you know, it's in the bottom group, it's in the group that's below that number. You know, the number I'm thinking of is in that group. So basically I've told you the whole half that it's not in. Okay, so let's say, you know, and you would naturally start with 50. So let's say I'm thinking of a number like 86 or something. So so you say, okay, you know, you might not really think it's 50, but you'll guess 50, because when you guess 50, you're gonna get rid of, well, you're either gonna guess right, or you're gonna eliminate half of all the numbers with just one answer from me. So you say 50, and I go, oh no, it's higher than that. Oh, well, you already have eliminated all these down here, and now we're talking about half the side area, half the number, half of the different possible answers. And then so it's higher, so then you might as well pick, well, let's in this example, let's say it's 32, okay, because that's what that's what this example is. So I'm thinking 32, and you guess 50, and I say no, it's lower than that. Oh, okay, so I've eliminated the top half, and now it's now you know it's between 0 and 50. So between 0 and 49, you know it's not 50, because you guessed 50, and I didn't say it, that was yes. So then you might as well divide that group in half, and you're going to guess 25, and then I'm going to say no, it's higher than 25, and then that eliminates half that way, and so now we're in this half, and we keep on going down until finally we guess it, and the maximum number of guesses is going to be log to the base 2 of 100. Log to the base 2 of 100 is about, well, 128 is 7, 64 is 6. Okay, so log to the base 2 of 100 is somewhere between 6 and 7. Let's say it's 7. So the most number of guesses is 7. And with 7 guesses, you're either going to say, well, in this particular example, there is a correct answer. If this were sparse, a sparse list, or a list of names or something, and you were just going with the alphabetical order, or some sort of sorted order, and maybe the thing you're guessing is actually not in there. Like, let's say it's a list of names, and you're looking for Joe, and Joe's not even in there, but the list of names is in alphabetical order. Okay, you can do the same sort of thing. Is it alphabetically, higher than, let's say, Michael? Is it alphabetically higher than Michael, or alphabetically lower than Michael, or is it Michael? And you'd say, oh, it's lower. Okay, then you get rid of all the names above and so on. But so in this case, in 7 guesses, you would be able to find the number, or you would be able to guess the number. All right, now here's a figure. Now, okay, so I don't know why both of these are exactly the same. I've stared at this for quite a while. I can't see any difference between 14.2.1 and 14.2.2. I mean, even these examples or numbers over here are the same. Maybe they're not supposed to be, but they ended up copying it in here wrong or something. But anyway, here is the function. They're both recursive. Yeah, they're both recursive functions. And so so we start with a number between 0 and 100, and we call this number, and gee, do we know where is the number in here? Okay, anyway, but this analyzes the this is the algorithm that you would do in your head if you were the person who had thought of the number. No, this is the algorithm that somebody else would be using to guess the number. And so you would start out with you would guess whatever the middle is, and you would say, is that the number? Is this middle one, is that the number? And the answer is going to be L, H, or Y. L means it's lower than that. H means it's higher than that, and Y would mean yes, you got the number. So so if it's neither lower or higher, then you got the number. Otherwise, if it's lower, then you go with between the low and the mid. This is low, this is low, this is high, this is mid. this is 0, this is 100, this is 50. Okay, so if the answer is in the lower half, then you, instead of doing 0 and 100, you're just going to do 0 and 50. Yeah, well, the forward double slash for division is it's integer division. We're all doing all integers, indexing indexes and so on. So it's convenient just to use the double slash for that. Yeah, you would, because you want an integer number, and in this case you may often get, if one of these is an odd number, then this is going to result in a fraction, right? Because if you have an odd number divided by 2, you get a remainder of 1. So anyway, yeah. Yeah, the double slash is interesting. That is a thing that varies in languages. I remember in programming languages before, well, there's always been the slash for divide, but Pascal, I think, was the first language that came along where they actually distinguished between, they had a different operator for for an integer divide, rather than, if you didn't have a different operator, you would just have to test. You would do a truncate, or you would do there would be a truncate function which would truncate, the digits to the right of the decimal point and so on. Then you would test if your result was the same as this truncated version. If it's not, then you know that it's not a whole number and so on. But yeah, and div. Some languages use the word div instead of double slash. Some languages use mod instead of a percent for the modulo operation. All right, so that's that example. And so here we're talking about this sorted list thing that I was telling you about, where here you've got a bunch of names, or you got 5 names, and they're alphabetical. They've been input in alphabetical order: Adams, Carver, Dolmer, Fredericks, and Lee. And so you're gonna you want to see if you're gonna enter a person's name, and then you want to find to see if that person is in the list. Okay, and if it's in the list, you want to give the index, is 0, 1, 2, 3, or 4. If it's not in the list, you want to say not found. So here, we're doing the same kind of greater than, less than thing, but and it's a recursive program. So we first we load it up. And is this thing something that we can run? I think we can run it later. And then here's where we call it. And this is the array of attendees. This is the name we're looking for. This is the lowest index, and this is the highest index. Okay, so this is 0 and this is 4, because this is 1, 2, 0, 1, 2, 3, 4. So this is the lowest index and the highest. So 0 and 4. And then we call this, and so we call it up here. This is the list of names. This is the one we're looking for, and this is the 0, and this is the 4. And so the range. So here we're testing the range size, and so this is how we're going to test to terminate. We're going to see if the range size is 1 and it's not equal. Okay. Okay, so, and the range is going to be the high minus low plus 1. Okay, so if it's, so let's say it's 0 and 4. It's 4 minus 0 plus 1. That's 5. So the range is 5. First one, the range is 5. And the middle one is going to be 4 plus 0 is 4 divided by 2 is 2. Okay, so the mid is 2. The range is 5. And so the first thing it asks for is the one you're looking for the actual the list at the list element at the mid that we're looking at. So this would be, let's say we're looking for Michael Carver. That's 1. That's index 1. So let's say we were so here if this were a 1, if we were looking at index 1, so Michael Carver would match that, and then we have an answer, we have a solution. It's that position, and then we're done. So then we can just return the POS. If the one we're looking for is not the list element that we're pointing to, okay, then if this is not true, it's going to drop down to this case, and this case tests if the range size is equal to 1. In other words, it tests if the range has only one element in it. If the range has only one element in it, and it's not the element we're looking for, well, then it's not in the list at all. So that's when we can set the POS to -1, the position to -1. Position to -1 means it's not the list. That's our signal that it's not in the list. If the range size is not equal to 1, in other words, if it's greater than 1, and we haven't found it yet, then we're going to do a recursive search, either the lower half or the upper half. Which is it? Well, we're going to test the item with the list, and if the item is less alphabetically, then we know we're going to have to recursively do another find on the lower half. If it's greater than, then we do the upper half. Anyway, so that's how this recursive recursively searching a sorted list. It's a binary search. If a sorted list has elements 0 through 50 and the item being searched for happens to be at location 6, how many times will the find function be called? Well, that's pretty, geez, you have to work this out. Okay, so the first time it's called, if it's between 0 and 50, the first time it's called, mid is going to be 25. That's 1. The second time it's called 25. What's half of 25? All right. So the next time it's going to be called, it's going to be between. Okay, so it's 25. So it's the lower half. So it's going to be between 0 and 25. Yes. So mid is going to be 25 plus 0 divided by 2 is 12. Okay, so that's 2. 12. At 2 we get. The second time we're at 12. Is it less than 12 or greater than 12 or equal to 12? No, it's less than 12. So then we do 12. Yes, it's less than 12. So then we do the lower half, and the lower half is going to be the midpoint of 0 and 12. The midpoint of 0 and 12 is going to be 6. So that sounds like it took 3 times. Now it could be off by 1, but it looks like we hit right on it. Okay, it is okay. So 0 and 50, and then it becomes 25. 0 and 25, it becomes 12. 0 and 12 becomes 6. Okay. So anyway, that's just test your understanding of that algorithm. That's pretty good. What's number 4 here? Adding an output. Oh, okay. This is a clever thing to do. This is interesting. I didn't really, I hadn't really thought about this until I saw it here. It's a way to, and I'm all for throwing in print statements to debug your code. Throw in some print statements and see where you are. See where you're at. See, you want to know what those values are at that point. You think you know what they are, and oh gosh, your thinking was wrong. So with recursive functions, the hard part is knowing, where you are in the nesting of the calls. And so your question is, can we use ceiling for an integer greater than or equal to? Okay, so ceiling would be, so if we're dealing with integers, we aren't going to have to worry about, because if we're dealing with indexes, then we don't really have to deal with ceiling or floor truncating. Oh, but when we divide, okay, you could. That'd be something you might want. That'd be something you could try. It might not work, but so what you could do is replace this here. So this is going to always do truncating. Let's say this ends up being an odd number. We're dividing by 2. Mid is going to be the truncated of, say this is 5. 5 divided by 2 is 2.5, and you truncate off the 0.5, and so you end up with just 2. If we were to change this and do a regular single divide, but then put the ceiling function around it, CEIL, so then that would round it up to 3. So that might be okay, because mid, instead of taking the 2, it's 5. We're looking for something that's halfway between 0 and 5. And in this case, the reason we do this is because we want an integer. We're talking about the index of a list element, and so it has to be an integer. But this is always going to give us the lower one. I think it would probably work if you always use the upper one. And when we get there, I'm going to try it. I think we're going to write something sometime. And it might not be in this chapter, but that's an interesting thing to try. That would be for languages that, and I'm not sure what the benefit would be, but it doesn't matter. It's an academically interesting question. All right, so here the way this works, the key to this working is each time you call a recursive function, you pass in this indent parameter, this argument, and whenever you print out anything, you print this indent first. And what this indent is some certain number of spaces, like 3 spaces. Okay, so here we're printing out. This is just some, here, we want to know what low and high is when we come in here, and so we're going to print out this word. We're going to print this out, and we're going to print out low and high, so we know what it is. But we're going to indent it by a certain amount depending on where we are in the nesting of calls. And so now whenever the first time we call, it's this one, we're just going to put in 3 spaces. That's the first time it's called. Okay, so it comes in here, and this is 3 spaces. Blah 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 blah. Now what's the next time it's called? The next time it's called is going to be either here or here. And so what we do here is we take it is the indent argument is going to be, the current indent argument plus 3 more spaces. So the next time it's called, it's going to be 6 spaces. This thing comes in, there's going to be 6 spaces now. So when this thing prints out, it's going to be 6 over. If it has to be called again, it's going to be 9 over. And so what happens is we see, the first time it's here, that's this right here, input. And then it's going to call, it's going to call find. It's looking for name, the one you just entered in this list that you just built here. And you're going to start with the 0th one and the number of attendees minus 1, so it's 4. 0 and 4, and it's 3 spaces in. So here we go. It's going to be it's here. It's find range, and then 0, and then 4, and 3 spaces in. So here it is, 3 spaces in, find range 0 and 4. And then it comes down here. Okay, so it prints that out, and then it's going to be it ends up being this. We didn't find it. The range is bigger than 1, so we go down here, and is the one we're looking for in the lower half, or is the one we're looking for in the upper half? Well, I can sneak and peek over here. It's the upper half. So this must have executed. And so here we're printing out searching upper half, same 3. It's the same 3. So here, searching upper half, it's here, searching upper half. It's the same 3 here as it was here, searching upper half. And then we call find again, but here we add 3 more spaces to indent. So then when we come back around and call and come back down around here again, this is going to be 6. And so this comes down through here, and so now we're in here. The first thing is this is 6 spaces, and then 9 spaces. And 9 spaces, they find it. No, they didn't find it after 9 spaces because the range must have been equal to 1, but we didn't find it, so it's person not found at 9 spaces. And then it says position equal to -1, and then this prints, and so then it goes down here. It doesn't call itself again. It just drops down to here. And it prints the same indent again, which is 9, and it prints returning position, and then whatever the position is, so it's returning this. Yeah. And then that returns, so this value comes back with POS. So in this thing, so it's going to return from it was upper half. So it's going to return from here, from upper half. And so this value is going to be what the POS was that was returned. And so that's going to be stored in here. And then it drops down here, prints that one, returns it back. It's going to be here again, returns it and ends up here printing not found, because if the POS that was returned from here is less than 0, then it's going to print the not found. But the idea here is this indenting thing, so you can really see it. You're indenting, and you're putting these print statements in here. This print statement in there to see where you are, and the high and low should be getting closer and closer together. And these other print statements is purely debug, purely for debug purposes. It's the real stuff is down here. It's either going to print out, you ask the person's name, and it's either going to say, I found it at a certain position, or I didn't find it. This is the real stuff. All these other print statements are just purely for debug, and I strongly encourage it. So what you can do is you can have a variable called debug, and if debug is equal to true, then you print out these print statements, and if debug is not equal to truth, then you don't print them out. And then you can, right here, you can just do if debug : and it turns out that you can actually put this print statement over here. You don't have to if it's just one statement. If it's then one statement, you can have it all in the same line. It's real convenient. All right. So here we are showing how this works, I think. Oh, this is the actual thing. We can test it. We can change the data. This is actually just this thing up here. So here I've got these people, and let's say I'm looking for Schmo, Joe, and yeah, upper half, of course, because Schmo is higher than any of them. And search 4 and 4. Nope. And the range is just 1, so it's didn't find it. However, if we're looking for Lee G or Jai, G, however you pronounce that, is found in position 4. All right, so the above debug approach requires an extra parameter to be passed to indicate the amount. Yes, you got to add some stuff there. All right, creating recursive function. Okay, it's 426. So so why don't I stop here, because this will lead real nicely into the assignment, that the 2 programming assignments that we're going to do. And so it's sort of some steps in actually creating a recursive function. You always have to make sure that you have a base case, and that's the terminating thing. That's what's going to make it start returning. And then you have to, so anyway, we'll go through all this in more detail next time. And then we'll start looking at, we will look at some functions that lend themselves very nicely to recursive solutions. Like greatest common divisor. Do we have greatest? Fibonacci is an interesting one. Calculating the greatest common divisor. That's a real common. It's common one. You should know how to do that. All right. So very good. Hope this helps. And next week is the next chapter is a 2-week chapter. So I might be able to squeeze the rest of this chapter into next week, depending on that, or I may have to have a two class period week. And so you're welcome to join me when I do that. In the meantime, keep up with the challenge activities and the lab exercises, and pretty soon we're going to start fiddling around with some other platforms and so on, and make this class a little bit more interesting. All right, that's all I have for today. So any questions?
I had a question. Do you ever do in-person classes? I mean, before the shutdown?
Oh yeah. In fact, yes.
Okay.
Yes, and I will, and I will again. I like okay, I really like having classes where there's something scheduled, because when there's nothing scheduled, so it's this semester I'm forcing myself to schedule, so that's why I make up this schedule every week. So, and it doesn't matter to me if I do my in-person classes at home or at school. And in fact, we got this new lab. It's this new room. It's at KCC now, where it's got a bunch of extra stuff, so you can do remote classes. What I I've always taught. I've always had my lectures available online live. Okay, so for the last 4 years or so, I've taught with the camera, and I've had a Zoom account, and before that I had a freeconferencecall.com account, and before that UH had this Blackboard system, and I had that. So so my favorite thing to do will be when school starts again, I'll have class, in the first floor of Copico, but you'll be able to attend remotely, and you'll also be able to watch videos later. There are people that like face to face. I don't know if that's why you were asking. I don't know if you really.
Well, I used to be in Copico all the time because you could brainstorm with other people.
Mm-hmm.
Coming up with ideas. And I thought, since the vaccine would be out and available, that maybe we can, eventually, maybe, the fall or summer, I don't know, but be able to do that.
I'm sure fall I'll be back there. So I'm sure I'll and I'll have some, it's kind of my choice. And so I will be sure to make sure that the class that you're in will be one that's actually a scheduled and have some face-to-face component to it, either all face-to-face, either it's going to be 2 2 lectures a week, or maybe 1 and, you know, sort of this hybrid kind of thing. But you know, we'll kind of see how that goes. But yes, I will be back in the classroom in the fall for sure. I'm getting my second shot, not tomorrow, but a week from tomorrow. So 2 weeks after that, I'm gonna feel safe. You know, I'll still wear a mask, you know, but yeah, I'm kind of looking forward to getting back in the classroom. This is kind of nice here in my office, but man, it's a mess. I'm glad the camera's only looking like this wide at this, you know, every
We can't see it.
Yeah.
Don't worry. Yeah.
Yeah.
But thank you so much for sticking through it, because this has been really unusual. I'm not used to learning online. So this book, Zybooks, really helps with online plus your lectures. So I just wanted to say thank you. And yeah.
Okay. Well, thank you for the compliment. And I will see you next week. Take care.
Bye.
Bye.